The Physics 30s. Okay, so we're going to go with the Compton effect practice questions here. So just like in the lesson, even though photons don't have any mass, they do have momentum, right? Because they have what we call a mass equivalency to their energy. Because essentially what mass is just energy behaving differently. So let's figure this out. So what is the momentum of a 500 nanometer photon? Okay, so we have a few formulas in the top corner there. So P is equal to H over lambda. And because we're talking about momentum here, we're going to have to use the 6.63 number. It's just the number we're going to have to use. And the wavelength is going to be in meters here. So just change that to meters. Okay, so it's a pretty easy formula. So you just punch that in. So we get a pretty small momentum. It just makes sense because it is pure energy. So why would it have a large momentum unless it was going really, 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 really fast? But it's a photon. It can only go one speed, sorry. If it has a really, really small wavelength, then it might have a large momentum. I always love this unit, the kilogram meters per second, even though it has no mass, just how the units work out. Photon A has a wavelength 3 times longer than photon B. Which photon has the greater momentum and by what factor? Okay. So we don't really know. We know that photon A is equal to 3 times photon B for wavelength wise. I'm just going to write that down like that. Okay. Which photon has a greater momentum? So using this formula, I noticed that the shorter the wavelength, the greater the momentum. So photon A has 3 times longer. So photon A is going to have a shorter wavelength, or sorry, smaller momentum. It's going to have a longer wavelength, smaller momentum, because they're inversely proportional to each other. So I'm just going to do this. I'm going to go photon A. Momentum is H over 3 lambda B, okay? And then photon B's momentum is just going to be H over lambda B, which makes sense, okay? Because that's just going to be B himself. Now, I'm just going to go back here. Maybe I'll just replace that with lambda A. So photon A, and then I'll do the substitution here. Okay, so now I'm going to compare these two together. I'm going to compare which one has the greater momentum. Okay, so you can put one into the other and then compare them that way. Okay. So what I'm going to do here, let's isolate for this one here. I could say, oh, actually, I'm just going to do this. I'm going to divide the two. I'm going to say B, the momentum of B, the momentum of A. I'm going to divide the two. So I'm going to go H over lambda B, H over 3 lambda B. I want to compare how much by what factor, so this is a good way to do it. So these are going to reduce out. These are going to reduce out. And I'm getting 3. So the momentum of B divided by A is equal to 3. So if I just slightly rearrange this, I could say that the momentum of B is equal to 3 times the momentum of A. You see that's switched around from the previous one where it says the wavelength of A is 3 times of B, but now the momentum of B is 3 times of A. Okay. So a photon has a wavelength of 6 times 10 to the negative 21 kilograms meters per second. What is the momentum of that? What is the wavelength and energy of this photon? Okay, so let's do its wavelength here. P is equal to H over lambda. Lambda is equal to H over P. I got to use the 6.63 number. That's a horrible number there. And There we go. Okay, let's see what we have here. So we've got 6.63 e to the negative 35 divided by 6e to the negative 21. So I get a wavelength of 1.11 times 10 to the negative 13 meters. Okay, that's a really small one. I'm not going to bother changing that to nanometers there. What's the energy of this photon? So I can use the hc over lambda formula to do that. I could also just use the P times C formula as well. So I can also use this E is equal to P times C as well. So I can use one of those if I have one or the other. So let's just use the second one there actually, because I have the momentum already. And I'm just going to times it by the speed of light. Okay. So if I use this one, I'm going to get 1.8 times 10 to the negative 12 joules. Not the best way to communicate this. If I change it into electron volts, I get 11.3 mega electron volts. It moved the decimal place 6 times there. If I moved it 6 times, I get 11.3. So if I use this one here, I can also just jump right into electron volts by keeping using the H value, that's electron volts version, divided by its wavelength, which I don't have in my calculator anymore. You get the same number, just slightly off a little bit. You can see there, the two numbers there. One's, well, you kind of see, one's 11.25 and the other one's 11.23. So we do lose a little bit of information depending on which one we use, because we don't have all the decimals of both of those numbers. So we just kind of lose. I'm just going to say we're going to use this one. Okay. And I'd be okay in that case, depending on which one you use. I don't care if you're off by 1 decimal place for these ones, because it's unavoidable sometimes. Identify the part of electromagnetism that this photon is. Oh, okay. So this is so I'm just going to go to my spectrum sheet that I have here. So on this page here, I have a bunch of wavelengths here. So what do we have? This is 10 to the negative 13. Kind of look like it's in the gamma or X-ray range. So maybe I can go over to this one here. Negative 13, yeah. So it's 12, 13. It's in the gamma range here. Okay, that's fine. So this is gamma ray. It's gamma ray. Yeah. What's the wavelength of a 100 kilovolt X-ray photon? 100 kilovolt X-ray photon. What do you want to find? The wavelength. Okay, so I'm just trying to figure out what we're going to do here. Maybe to combine these together. Oh, we don't have to combine these together. I was thinking, we're in the Compton effect way. Maybe there's some kind of momentum way to do this, but why would you do that when I could just use E is equal to HC over lambda. Lambda is equal to HC over E. And if I just use the 4.14 number, and I change that one into 100,000 electron volts, I'm going to get a wavelength of 1.24 times 10 to the negative 11 meters. I thought I had more Compton effect, like angle questions on here. Yeah, that's okay. So an X-ray photon strikes a helium nucleus, an alpha particle, and bounces straight back. So that's going to be key. It bounces straight back. So if it bounces straight back, that means my deflection angle for theta is 180 degrees. So this is the largest it could be. I'll calculate the velocity. If the helium nucleus is originally at rest, what's the velocity after this interaction? Okay, so what I want to do is I want to determine how much energy the photon loses Because if it loses energy, it's got to go somewhere, so I'm going to assume it goes into the helium nucleus. So to find out how much energy the photon loses, I'm going to determine how much wavelength it changes by. That's a weird looking lambda. Okay, so I'm going to go HC over, or H over MC, 1 minus cos 180 degrees. So you have a little bit of theta there. Cool. So my H, I'm going to use the 6.63 number. My mass is the mass of a helium nucleus here. 6.65 times 10 to the negative 27. Yeah, it's on the formula sheet. The speed of light, obviously, is the speed of light. So if I punch these all in there, H 6.63 divided by 6.65 e to the negative 27 times speed of light times 1 minus cos 180. Making sure I'm in the right mode. I'm in degree mode. That's good. So this should be 2 times that previous number because 180 is negative 1. So 1 minus negative 1 ends up being 6.6466 times 10 to the negative 16 meters. Okay. So the wavelength's not going to change that much. It's a really small change in the wavelength. Okay. So what I'm going to do now is use that wavelength to calculate the energy. Okay, so since the energy and the wavelength are inversely proportional to each other, I can't just convert this change into energy and expect to get the right answer. I don't think you can. So what I'm going to do is I'm going to find out the two energies, the before and after of the photon. So before the collision, the energy of the photon, let's see what this is before. Okay, I'm going to do HC over lambda. I'm going to use the joules because eventually I want to do this calculation for velocity. So I'm going to want this in joules to do that. So I'm going to go 6.63 times the speed of light divided by the wavelength in regular meters. So I'm going to just change that there. So I'm going to get joules, 1.989 times 10 to the negative 14 joules. Okay. Now afterwards, it's going to be HC over the lambda plus the change in the lambda. Okay, so that's not going to be too much of a difference between the two. So I'm going to take that nanometer one, that one we just did, and I'm just going to add in my change. I think that's what that number is there. Yeah. Okay. Add in my change here. So it's not going to change too much. Like the energy here is only going to be slightly lower. So it's 8.8676, etc., etc. Okay. So the change in the energy is just going to be the final minus the initial. So I'm going to subtract those two numbers there. 1.898 e to the negative 14 minus this number. And what I'm going to get is I'm going to get 1.3. I'm not too concerned about the negative in this situation. 1.3219 times 10 to the negative 18 joules. So my photon loses that much energy. Where does the energy go? Well, it goes into the kinetic energy of the alpha particle now. So I'm just going to put a line here. Okay. Put all that effort to wiggle in, it just straightens out for me. Okay. So the EK of the alpha particle now is equal to 1/2 mv squared. So that's going to be 2 times the EK divided by its mass, all square rooted. So 2 times this number that we just have here, divided by the mass, What's the mass again? 27. And then take the square root. So I'm not going very fast, but fast enough. So 19,900, so 10 to the 4 meters per second. There you go. Hopefully that was, hopefully you did well when you did that worksheet. And I'll see you in the next video. Bye.